Here to you today. It's good that I consulted with our speakers beforehand to find out how they wanted to be introduced. I was going to introduce our first guest today as Andy Lewis, but he told me that he just prefers to be referred to now as Andy. So apparently, he's a one-name superstar in the tradition of Madonna and Beyonce. I have the pleasure to introduce to you Andy from the University of Leeds, who will be speaking about the complexity of computable categoricity.
I didn't really mean that. Okay, so I'm going to talk about some work that a bunch of us did earlier on this year, which is to do with computable structures and specifically computable categoricity. Okay, so I'll talk in some detail in a little bit about exactly what it means for a structure to be computably categorical. Okay, so basically, a computable structure is computably categorical if for any two computable copies of the structure, there's a computable isomorphism between them. Okay, so in other words, so a computable structure is computably categorical if for any other computable structure, if it's isomorphic, then it's computably isomorphic. So computable categoricity is a sort of fairly central notion in the study of computable structures, and it's been a long-standing question. So how hard is it to decide whether or not a structure is computably categorical? So what we're able to do is basically to show that it's it's as hard as it could be, basically. So the index set is pi11 complete. So what I'm going to do today, I'm going to first of all, I'm going to give a bit of an introduction to the area, and then I'll say a little bit about the proof without any technical details. Okay. So, right back to the beginning. So we'll talk about computable structures. What is a computable structure? So it's just exactly what it has to be, right? So it's just a structure in which the domain and the relations and functions are computable. Okay. And then if you're working with computable structures, there's a sort of basic question which pretty much immediately arises, which is, so we have two different computable structures which are isomorphic, then to what extent can we regard these things as being the same? Right? The point being that maybe they're isomorphic, but there's no computable isomorphism between them. Okay. So that motivates this definition then. So we say a computable structure is computably categorical if whenever two computable structures are isomorphic to it, there's a computable isomorphism between them. So it might seem like I phrased that in a slightly odd way. That's in order that the relativized version will explain later. Okay, so that's sort of fairly clear. So some simple examples there, very simple examples. So we just take the natural numbers with the successor relation. That's obviously going to be computably categorical. If I take two computable copies of that structure, you're given like the finite amount of non-uniform information where 0 is, then you can just compute the successor function to give you the isomorphism. Okay. And then another very simple example, we just take the rationals of the standard ordering. That's going to be computably categorical just by the normal back and forth argument. Okay, so you construct an isomorphism stage by stage, and at any given stage, you've already decided this tuple in the first structure should be mapped to this tuple in the second structure. You want to decide where to map this guy is in between these two guys. You say, well, wherever I map these two, just find some guy in between and map it to there. Okay, so the whole thing goes through in the computable fashion. Okay, so we want to understand. So what does it mean for a structure to be computably categorical? And ideally what we'd like is a nice sort of simple syntactic or structural characterization of the computably categorical structures. Okay, so as an example of what I mean by that, so if we restrict to sort of specific classes of structures, then sometimes we can get a very nice characterization of computable categoricity. So if we talk about computable linear orders, for example, then they're computably categorical if and only if they have finitely many adjacencies. So finitely many pairs of elements A and B, such as B's above A and there's nothing in between. If we talk about computable Boolean algebras, then they're computably categorical if and only if they have finitely many atoms. Okay, so for these specific classes, we get a nice characterization, but can we do anything like that in general? That's the question. So if we strengthen the definition slightly to give a very similar sounding notion, which initially looks like it might even be the same sort of thing, then, I mean it's not the same, but initially maybe it looks like it could be, then we do get a nice characterization. Okay, so here's the definition. So we say a computable structure is relatively computably categorical if for any two structures A and B isomorphic to it and where they needn't be computable anymore, There's an isomorphism between them, which is computable in the oracles. Okay, so computable in the O plus of the atomic diagrams. So that's a slightly stronger definition. And then we can weaken that definition if we want in a fairly obvious way. So we say, so a computable structure is relatively delta zero alpha categorical. If for any two structures A and B isomorphic to it, there's an isomorphism between them, delta zero alpha in the O plus of the oracle. Okay, so for this definition, which initially you sort of think could be the same thing. Anyway, for this you can get a nice characterization, which is due to Goncharov. So for a computable structure is relatively completely categorical, even only if it has a C-Scott family of existential formulas over a fixed finite set of parameters. So what does that mean? So Scott family is a simple object, right? So Scott family is just a family of formulas such that any tuple in the structure has to satisfy at least one of the formulas. And for any one of the formulas, if any two tuples in the structure satisfy that formula, then they're actually automorphic. Okay, so it's a family of formulas that defines the automorphism orbits in the structure. Okay, so in this case then, so we have this nice characterization, and that immediately tells us that being relatively completely categorical is not that complicated. It's sigma 0, 3. Okay, and in fact it's sigma 0, 3 complete. So then the immediate question is, okay, well, is that the same then? Maybe being relatively computably categorical is the same as being computably categorical, in which case we're done, right? We've got a nice characterization already. But so Goncharov showed that's not the case. You can have computably categorical structures that are not relatively computably categorical. Okay, they don't satisfy the stronger definition. They are actually equivalent if you restrict yourself to two decidable structures. Okay, so two decidable means that the two quantifier diagram is decidable. And then the assumption of two decidability there is necessary. It's not the case for one decidable. We have one decidable structures which are computably categorical, but not relatively computably categorical. But then they do have to be relatively delta 0, 2 categorical. Okay, so initially it looks like there's a sort of pattern emerging here. So if the two decidable are the same, if you're one decidable, then computable categoricity implies relatively delta 0, 2 categorical. So you might guess that if you're computably categorical, you have to be relatively delta 0, 3 categorical. Okay? But this is not the case. In fact, it fails as strongly as you can imagine. So the first theorem there is that for every computable ordinal, there's a structure which is computably categorical but not relatively delta 0 alpha categorical. Okay? So it fails very strongly. And in fact, more than that is true. The index set is as complicated as it possibly could be. It's pi 1 complete. Okay? So actually, the second theorem there implies the first one. Why is that? Well, so what is the definition of computable categoricity? It says a structure is computably categorical if for all other computable structures that you're quantifying over numbers, like indices, if there exists an isomorphism, then there's a computable isomorphism, right? So initially it looks like you have to search over all isomorphisms, and in fact you do. But if the first two failed, then you wouldn't. You don't have to search over all. So for some ordinal alpha, some computable ordinal alpha, you'd only have to search over delta 0 alpha isomorphism. Okay, so what I want to do basically is to sketch the proof of the second theorem. But the way in which you prove the second theorem is to prove the first theorem and then apply an overspill argument. Okay, so what we want to do, first of all, we just want to prove the first theorem. So for given any notation, say for a computable ordinal alpha, we want to build a structure which is computably categorical, that's one of our tasks, and which is also not relatively delta 0 alpha categorical. I think that's our second task. So initially, let's concentrate on the second task. How do we do that? Well, as we saw before, there was this nice characterization of relative computable categoricity, and that extends in a fairly obvious sort of way to give us a nice characterization of relatively delta 0 alpha categorical. Okay, so we can use that. So that's due to Ash. So this is basically the same thing as we had before, but now with delta 0 alpha in there. Okay. So for a computable structure S, the structure is relatively delta 0 alpha categorical, even though it has a C-Scott family of sigma alpha formulas over a fixed finite set of parameters. So the C there indicates that we're talking about computable infinitary formulas. Okay? So if you're familiar with those, then good. If you're not, it doesn't really matter because we're not really going to be dealing with them in a detailed way in this talk. Okay? So most of the details though aren't really important. So basically, what do we take away from this? If we want to build a structure which is not relatively delta zero alpha categorical, then it suffices that we ensure that there are non-automorphic elements in the structure which satisfy lots of the same formulas. Okay, in particular, all the same computable infinitary sigma alpha formulas. But anyway, so we want to build a structure in which we have non-automorphic elements and that satisfy lots of the same formulas, right? So we better choose a particular way of doing that. So let's start off very simple. Let's just think about existential formulas. Okay? So we want to build a structure in which you have two non-automorphic elements that have to satisfy all the same existential formulas. So how can we do that? Well, there's one way we can do that. So we start off, so our domain, okay, is just a set of strings of natural numbers of length, and so not empty strings, let's say, of length less than or equal to 3. Okay? And such that you don't have equal adjacent bits. Okay, so you're not allowed 001 or 011. Okay, so just all strings of natural numbers of length less than or equal to 3, and you're not allowed adjacent bits. Okay, that's the domain. And then we form a structure out of that. So we form like a labeled graph. Okay, so the nodes of the graph are just the strings, and then we put an edge between two strings if one is a one-element extension of the other. Okay? And then we put some labels on the leaves, and the labels we put on the leaves are just labels that indicate the last bit. Okay? So from each string, you can sort of see the last bit in some sense in this structure. Okay.
Andy?
Yeah.
I'm a little confused in the first diagram. 0 has two successors, both of which are labeled 1.
Yeah, well, okay, this is good. This should be a dot, dot, dot then. So 0, 1, and it could be 3, 0, 1, 3, 0, 1, 4. But there should be more, it's hard to draw a tree. Yeah, that's it.
Well, no, you have two ones next. Should it be 0, 1 and then 0, 2 next to it?
Oh, I see what you mean. Yeah, right, yeah, right. Yeah, okay, so yeah, you're right. 0, 1, 0, 2, yeah, yeah, you find out problem. Yeah. Okay, so it's the structure. Clear? Yeah, we're basically all strings of natural numbers are less than or equal to 3. And then we form the structure without equal adjacent bits. We form a structure, we form a labeled graph out of it in this way. So you put an edge if you're a one-element extension, and then we label the strings of length 3 with the last bit. Okay. So then, okay, some terminology. So I'm going to extend to ordinals in a little bit. Okay, so I'm going to talk about things of rank. So rank 0 is the top row there, rank 1 is the next row, and rank 2 is this row. Okay. And then a little bit of notation for any string sigma, by a sigma, I mean the part of the structure above sigma. Okay, so if sigma is just 0, that's kind of this part of the structure up here. If sigma is 1, it's this part of the structure. Yeah.
On the predecessor or
Prefix
relation, what's the structure, the relations?
So just imagine this little thing. If sigma is 0, the structure would be this.
What's the signature?
So you have an edge relation and you have the labels on the So imagine you have a different relation for each number, which is a different kind of label. Yeah? Okay. Okay, so some obvious observations about the structure. Okay, so if two strings end in a different bit, then they're not automorphic, and the substructures they give rise to are not isomorphic. Okay, that's kind of, you can see that fairly clearly just by working down to induction on the rank. If you start at the top, if you end in a different bit, you're obviously not automorphic, because you've got a different label. Right? And you work down from there. Yeah, okay, so, and I'm going to draw out this particular fact. It might seem strange that I'm sort of phrasing this way. It's going to sort of sound the same later on, okay? So in particular then for siblings, by siblings I mean strings which are the same except in the last bit. Okay? So for siblings, sigma 0 and sigma 1 are finite rank, well everything's here a finite rank, so it seems silly I'm saying that. Okay. For siblings of sigma 0 and 1 of finite rank, the corresponding substructures are not isomorphic. Okay? It's a simple fact that's fairly obvious in this structure, we're going to have that in more complicated structures. Okay, that's the first observation, and then the second observation is that elements of rank 2 satisfy the same exponential formulas. Okay, so this is an element of rank 2, these are the elements of rank 2. So any sort of finite structure you can embed in here, you can also embed in here. Basically, it's by going far enough over to the right. Okay. So, in this structure, what do we get? We have these two elements here are non-automorphic and they satisfy the same exponential formulas. So that was working with strings of length 3. If we work with strings of length 4, we'd have two elements that are non-automorphic and satisfy the same sigma 2 formulas. Okay, you can continue that up on through the natural numbers. And in fact, if you fiddle around it with it a little bit, you can get it to work through all the computable ordinals. So in summary then, we get a standard way of producing, given any computable ordinal alpha, a structure which is not relatively delta zero alpha categorical. Which isn't that much of an achievement, because we need to make it completely categorical, right? But anyway, we have a standard way of doing that here. And the structure that we get still satisfies the equivalent of the condition we isolated for the finite case. Okay? For siblings, sigma 0 and sigma 1 of rank beta, say, the corresponding substructures are not isomorphic. Okay, we get that fact. So again, it might seem a little bit weird. I'm putting that fact out, but we're going to use it later on. Basically, siblings give rise to non-isomorphic substructures. That's the fact. Okay, so then we know how we're going to go about making things not relatively delta zero alpha categorical. Now we want to make sure that they're computably categorical. Okay, so in order to do this, there's well, there are a few different ideas needed, but the basic idea is pretty simple. Okay, so the basic idea works roughly as follows. So first of all, we establish a notion of expansionary stage. Okay, well, actually, first of all, what do we have to do? Right? So we're building a computable structure A, and for any other computable structure, if it's isomorphic, we have to make sure it's computably isomorphic. Right? So for now, let's just focus on one particular computable structure. Imagine as we're building A, we're watching G. If it's isomorphic, we have to make sure it's computably isomorphic. Okay? So the first thing we do is we establish a notion of expansionary stage. Okay? So as we're constructing A, at some point we draw a line in the sand and we say, as soon as this much of A appears in G, we'll have what we call an expansionary stage, and at that point we'll build some of our isomorphism. Okay? And when that expansionary stage happens, we draw another line in the sand and we say, now, if this much of A appears in G, then we'll build some more of our, for an expansionary stage, build some more of our isomorphism. Okay. And we use this system of labeling elements of the structure. Okay, so what we do is so labels, when they're given to an element of the structure, initially serve to uniquely identify that element. Okay, so the idea is you give a label to an element of the structure, he's the only one who's got that label, so he's uniquely identified by that label. But then we also have a bag of labels. Okay, so initially you give a label to an element, later on you might add it to the bag of labels. And what that means is, at that point, when it enters the bag, you give that label to everybody. Okay, so now that label isn't serving to uniquely identify anybody. Right? So initially it uniquely identifies the element. Once you add it to the bag, it doesn't anymore. Okay, so here's a little picture. So we've got, this is an element in A, right? There'll be lots of elements in A. It's a particular element. These are labels that we've given to it, and the ones I've crossed out are ones that are added to the bag already. So they're not serving to uniquely identify this element, but the other ones are. Okay. So we wait for an expansionary stage. An expansionary stage, something in G has to appear with these labels, right? You have these uniquely labels identify that element. So at that point we say, right, we're going to map this guy to this guy. Okay. So we're starting to build our isomorphism. And at that point also, we add one more label to the bag and we give them a new label. Okay, and then we wait for another expansionary stage. At the next expansionary stage, which guy has to appear with his labels again? Well, it has to be the same guy. Right? So what's the result of the process? Well, okay, if there are only finite many expansionary stages, that is not isomorphic. If there are infinitely many expansionary stages, then we build an isomorphism stage by stage, and the isomorphism partial isomorphism that we built at any expansionary stage properly extends the one at the last expansionary stage. We really do build an isomorphism. And what's the result? What happens to all these labels? Well, if there are infinitely many expansionary stages, they're all getting added to the bag of labels. Right? So in the end, they're not serving to uniquely identify the individual element. Okay, so we're going to be able to maintain this fact that they satisfy a lot of the same formulas. Right? It doesn't screw up what we're trying to do before. That's the basic idea. Okay, so using that sort of basic idea, a few others, we get a method which produces, given a notation for any computable ordinal alpha, a computable categorical structure which is not relatively del zero alpha categorical. Okay, so that's theorem 1. And this structure still satisfies the same basic condition that siblings give rise to non-isomorphic substructures. Okay. So now let's see the overspill argument. So in order to make that work, what we've done, we've given notations for computable ordinal alpha. We have to produce a corresponding structure. Okay. So now we have to work with an extension of O, which is O star. Okay. So what is O star? It's basically, so when you define O, there's a C relation, which when restricted to O gives the ordering on O. Okay. If you take all of those numbers, all of those notations for which the set of predecessors according to that relation gives a linear ordering without any hyperarithmetic descending sequences, then that's O star. Okay. So what does O star look like? It basically looks like O with some extra elements in it. And if you're one of the extra elements, and you've got a maximal path row below you, and some linear order above that without any well-ordered initial path. So the important point here, one of the important points is the last one here. So there's a computable sequence of limited, well, it doesn't matter the limit element, but there's a computable sequence of elements, alpha n and O star, such that the set n, alpha n and O is pi 1 1 complete. Okay, so for any pi 1 1 set f, we can get a computable function which, given any n, will produce something in O if n is in S, and something in O star not in O if n is not in S. So now we have to produce a structure given any notation in O star. Okay? And what we want is the following. So when we're given a notation in O, we get a computable categorical structure. When we're given a notation O star, we want it not to be computable categorical. So here's the first observation. Okay, if we run the construction for given a notation in O star that's not in O, then this sibling condition fails, in fact. So ignore the fact that there's successors there. For beta less than alpha, they're in O star and not in O, siblings of rank beta actually are isomorphic. Okay, but you can use the existence of an infinite descending sequence below beta to build the isomorphism. Okay, and then just a little bit of notation. So A sigma stroke sigma prime is the structure you get by replacing what's above sigma with what's above sigma prime. So now let's see the overspill argument. So so we're given this alpha, right, which is an O star and not an O. And we're considering the structure that's built on this given that alpha. Let B be the set of all successors beta less than alpha, such that there's no computable isomorphism between any siblings of rank beta. Okay, so first of all, this is an arithmetically definable set. Okay, so alpha is just a notation. All the stuff that's less than that is CE. Having a computable isomorphism, that's sigma 0, 3. Okay, so this is an arithmetical set. But then it certainly includes all the beta less than alpha that are actually in O, because things that for siblings of rank beta and O, they're actually not isomorphic, so there's certainly no computable isomorphism. Okay. So this is a set which includes a maximal path through O, but which is arithmetically definable. Okay, but we don't have arithmetical maximal paths through O, so we have to include some extra stuff. Okay, so there must be some beta 0 in this set, which is in O star and not in O. Okay, so then we just let sigma 0 and sigma 1 be two siblings of rank beta 0. So their corresponding substructures are isomorphic, but not computably isomorphic. Okay. Then we take A, and we take the structure that we get just by replacing what's above sigma 0 with what's above sigma 1. And these are both two computable structures. They're isomorphic, but they're not computably isomorphic. Okay. So hence, A is not computably categorical. Okay, so then basically we're done. We just have to use this fact before that we had this pi11 complete. That for any pi11 set S, we can have a computable function which gives you n in O if n is in S, and n in O star and not in O if n is not in S. Okay, so we can produce a structure which is either computably categorical if you're in S, or not computably categorical if you're not in S. Okay, so stop there. Thanks.
Thanks, Andy, for your talk. Are there questions? Well, I have a question. If you know, what would be the next theorem?
So the question whether you can produce structures which are computably categorical but not hyperarithmetically, relatively hyperarithmetically categorical. That's, I guess, that's still open. Not that I intend to work on that. But.
Yes. Oh, sorry.
And you started out the lecture by saying, for two specific structures of linear ordering and Boolean algebra, you had a characterization, somebody had a characterization of when they're computably categorical, right?
Yeah.
Okay, so now forget about relatively categorical, et cetera, delta 0 to forget about relatively computable categorical, just basic question for computably categorical citable structures in the base case, but structures other than those two. Is there anything there?
Yeah, there's various other stuff like abelian groups of torsion-free abelian groups of completely categorical if they're a finite rank. There's other stuff about trees, finite trees and stuff.
Equivalence relations.
Right. Okay.
Trees are finite height.
Okay. There are, I think, yeah, there's quite a few
But
examples.
it basically is wide open.
I think there are quite a lot of examples. No, and I'm not sure the extent to which there are lots of open questions.
So they don't have to do with pi11 sets and O and things like that. They have to do with more specific concrete things. Can you muscle your way through computable isomorphism or not? Right?
I think, what did you say, sir?
Okay. The results for the base case of computably categorical structures do not have to do with pi11 sets or paths or things like that. They have to do with, just can you.
Yeah, well, they all have to. I think that for all the examples that are known, basically the reason you get the nice categorization is because in that instance, relative computable categoricity coincides with computable categoricity. So there's a kind of basically a nice categorization, relative computable categoricity, and in some cases that turns out to be the same. That's the basic situation as far as I'm aware. Anyway.
You have some results, you don't, but some other people have results for these basic structures using Goncharov, using Scott sets, using analysis of the formulas that hold or not hold, right?
Yeah.
But it looks like it's just the beginning. It looks like, I mean, if you look at the classification of finite simple groups, it looks like it's just starting.
Yeah, well, I mean, to a certain extent, what we're showing here is, for computable categoricity, you can't get a nice categorization, right? I mean, what you've shown that the index says pi11 complete, all of those examples, you're getting like nice sigma 03 definitions, right? So in this case, we've kind of shown you can't get a nice characterization for the computable categoricity, I guess. Depending on what you mean by nice.
There's a whole bunch of things that you can probably code this into. This is Grax, of course, but there's a whole bunch of things you can code things into, like, shown by Slinko and Husayinov and others, maybe Goncharov, that if you can do this coding, you could probably code it and get the same answer there. So in some sense, there's a bifurcation between things which are unclassifiable and things where we understand them quite well.
Okay, so the pi11 thing says that these things are complicated and we can't get a nice classification, but we don't have a theorem like finite simple groups in which we have an absolute complete classification for.
Well, this says you can't.
Um,
This says you can't. That's the point of the theorem. If something's pi11 complete, you can't classify it. That's the deal.
Okay, I mean, I'm not sure that, so it says you can't decide of a given object whether the answer is yes or no, but.
Well, I mean, you could, one classification is the isomorphism types. So that's not going to do it, right? I mean, anyway.
So let me ask one more question here. Some of your results are not uniform. Like to get the isomorphism, if you have the natural numbers with successor, is non-uniform choice. What's the zero? Have there been any results along the lines of uniform, computable?
Yes, you can't do what we're doing. In what we do here, the reduction can't be uniform. So I think if the reduction is uniform, it has to be computable categoricity. Has to imply relative computable categoricity or relative delta 0 2 categories or something like that. So yes, we know that you can't do that here.
Okay. Well, let's thank the speaker again.